off we go. So hash tables, we know there's a nice way to do it so that you don't have to worry too much about collisions. We are going to do open hashing, also called separate chaining, where if ever our hash function takes us to the same index for something, we're gonna just reuse that index. Put not just one thing there, but put a list of things there. It's always going to be key value pairs, all the things that hashed to that bucket. All right, remember the terminology. And yeah, we saw a little example. Let's keep going from there. Because say we've got a hash table, we're using open hashing, we should also be allowed to remove some stuff. Like, okay, I put the number in, but somebody, I don't know, the number went out of service. I don't know, the business doesn't have a phone number anymore. So we need a way for removing things. So that is a very simple idea, and it's going to look as you would expect. So if we're doing open hashing, this is what our hash table looks like. It's got, I don't know, some stuff. Every index is a list of key value pairs. I don't know, let's say that most of these are empty. I don't know why I drew so many, but like you got something here, like something hashed to index 0. Maybe that was my phone number. So it's a list of pairs, and then maybe my mom's phone number hashed to over here. Boop. Close that off. And say you want to remove me. I don't know. I got a new phone number, or I'm not your teacher anymore. You don't want me in your phone book. What you'll do is you'll go as if you're searching for it, right? You'd go to the index where it's going to take you. Like if you were inserting it or searching for it, you go to that, you'd hash the key, my name, and then you go looking through that list for the key value pair with the key equal to the key you want to remove, right? Because that's where it would have gone, would have been placed if it was there. If you find it, just remove it from the list. You know how to delete stuff out of lists. Just do it. And then now that turns into an empty list. It's honestly not too bad once you remember how to delete stuff from lists. You just use the C++ list erase operation if you don't want to make your own linked list. So that'll work. Does that make enough sense? Just go in, get rid of it. That's where it would have been had it been inserted. If it's there, get rid of it. If it's not there, you have nothing to do. You'll have to search for it though through your list. Okay. So yeah, with that, we have like the three main ways of doing stuff with open hashing. We know to look up, we just go to the index where the hash function takes us for our key, go get the resulting, get the corresponding value back. There should only be one. For insertion, the way we keep it only one is that we go and we look through the list. We do the hash of the key. We're about to insert a value. Make sure that there's no version of that key already in the list there that we find at that index. If there is one, replace the value. If there isn't one, go and add a new key value pair. And then now we know how to remove. So let's talk about the complexity of all this stuff. So let's do the worst case, because the worst case is still not going to be perfect. It's going to be not constant. Though I've claimed, right, we get constant stuff out of the deal, and it's going to be in the average case, actually, that we get constant time. So interesting to think about. Not really average case analysis is the topic of this class, but at least for hash tables, it's important to go there. So yeah, let's do the worst case complexity, because we can understand how to do that. So let's say that we've got capital N for us now means the number of key value pairs that we have inserted into our hash table. Like that's the size in terms of those. And so in the worst case for running time, like you have a couple options, right? It's really like collisions are your enemy when it comes to time complexity. So what will cause a lot of collisions? Either a very small table where you are forced to go to one of a couple indices and you're inserting more things than there are indices, or your hash function is horrible and it's sending you to the same index way too many times. All right, so that'll give you a lot of collisions. Like let's say this is my hash table. No matter how good your hash function is, it's only going to ever take you to index 0 or index 1, right? When you string stuff down. So if you're putting n values in this hash table with two things in it, in the best case, each of your lists holds n over 2 things, right? And that simplifies big O of n, right? So there's big O of n things in each of these lists here in that case. So this is worst case, right? Usually you're not going to be in this worst case. That would be bad programming, okay? So that's just like O of n nodes per list, and you better believe that you're going to have to search through one of those two lists with O of n nodes in them to do things. So like for insertion, right, you have to do the hash. It's taking you one of your very few indices, or you're colliding. You're getting to a list that's really long, all right? You're searching. You got to search for the key that you want to go and insert, because maybe it's already there and you have to update it, right? That searching process makes it O of n, okay? You could make that a little bit faster by just doing always pushback, assume it's never there, but that is at the expense of lookups time complexity, right? Because if it was there, then what do? Go look at the end first. And also the space. Now you're adding space, now you're duplicating things every time you want to change a value. So that's a little disgusting. So it's probably the best trade-off to do it the way we're doing it. So that is going to turn into linear time search in the very worst case. Does that make sense to us? This is, a lot of things have to go wrong to get here, but this is the worst case. Yes? That's the idea for that one. And then everybody who's got a bottleneck, or everybody who has search deep down has that same bottleneck. So like for lookup, you want to get the value associated with the key. Well, you hash your thing, you get to a list, one of these two in this case, right? In the worst case, you got to search for the key, get the value back, or like throw an exception or something if it's not there. That searching process again, in the worst case, you're going through all the entire nodes in that list. Yeah. All the pieces there, key value pairs, maybe it's not there. You got to get through it all. So that is, again, a linear time deal in the worst case. So because of search, it's linear time for lookup as well. And then you're going to search for removal, and you can imagine it's going to be linear time for removal too. So unfortunately, we've got linear, and linear worst case complexity. Oh no. But space complexity at least is, you can't really mess that up. You're storing n pairs of things. So usually in most implementations of hash tables, including the one in the C++ standard library, they don't let the table size, because like you do have a table of potential pairs, right? Some of them might be empty. For example, a table of lists, most of them might be empty. But you're not going to let the table size get too much bigger than like some constant multiple event, like 2 times the size, 3 times the size. There might be some resizing necessary as you insert things, kind of like a vector. But that's not going to change the space complexity. Like you're holding n things, maybe you have room for 2n more or something. It's still proportional to the number of things that you've inserted. So it's linear space complexity for the entire data structure. It's honestly, you're getting better space complexity if you have a very small hash table that's so tiny, but that's at the expense of time, right? So yeah, any questions about that analysis? Does it make sense why that's going to be the worst case? You'd usually never run into it, the worst case like this if you made a larger hash table, but this is something that could happen, okay? So each of these indices, what did they have? They had O of n things. Oh no. Sad face. So yeah. The average case, though, is where hash tables shine. All right? So let's think about this. In the average case, I'm not really going to teach you how to do average case analysis. This is all hand-wavy on this slide, but it's still useful. So in the average case, on average, like say your hash functions, like it's trying to send everybody to different places as good as it can, right? In the average case, your values are going to like, you got, I don't know, I indices and n values. You're going to put I over n values at each index. Yeah. Something like, or sorry, n over I. Math is hard. You put that many things at each index. Something like that. That's what's going on, right? So your values will be split evenly on average. I think you can imagine that's what's going to happen. Like you've got 1, 2, 3, 4, 5 indices. Like your hash function on average is probably going to, like, you're putting 5 things and it's going to do that. You got 6 things, it's going to double up somewhere. Probably not too many places then. Something like that, all right? So that's, you can imagine if you have a good hash function, it'll do that. Assuming your table is like size proportional to the number of things you're inserting, then you will store then a constant amount of things at each index, right? That is key on average, all right? On average, like you've got, I don't know, I indices, n values, something like that. So it's like n over I, where I is the number of indices. And those should be that will end up being some sort of constant. So that is because I is proportional to n, right? That's the goal. So let's deal with that. So yeah, for example, let's say that our table size, just to bring that point home, table size is like, I don't know, we always keep it about twice the size of the number of things we're going to insert, like 2n. In that case, then, how many things on average will be at each index? Well, it's n things out of, and you're sharing it among 2n indices, then you'll have about half an entry at each index, something like that. That's kind of what you want, smaller than 1 if you can. And if there's a constant number of things at each index, that means there's a constant number of elements per list, right? And now what does that do for everybody who's trying to search through those lists? Lookup, for example, you're searching through a constant number of nodes. Ta-da, we have linear time, right? And for that same reason, insertion, where search was the bottleneck, removal, where search was the bottleneck, now we have, on average, a constant time search through every list. Hoo-hoo. And then all the extra work, like removing from a list and doing actual insertion, like pushing back or something, that's still constant time. So constant. Everything becomes constant. Does that make enough sense to us? Any questions about that? Average case analysis, but pie in the sky dream, that's kind of what's happening, right? On average. And we get constant time out of the deal. And that's usually the case unless we do something weird with our hash functions or force a very small table on ourselves. And yeah, again, still, usually our table's not going to be much larger, not much bigger than the number of things we're putting in it, like twice the amount, 3 times, 4 times the amount, something like that. And so we're still going to have proportional to n list indices with lists in them, and the values that we place in the list as well will have n things total. So that is going to be still linear space complexity, which is as good as you could ever hope for. Can't do better than that. Okay, so that is wonderful. That is the analysis, and I think that's what I wanted to say. Any questions about any of that? So you did worst case. Oh no. Average case. That's not horrible. Okay. And usually I'll run into the average case, of course. All right. So I'll give you this analysis. Here's the running time worst case complexity analysis. I have a question for you now. So we could do better. Like, let's say we're talking about lookup. Like, what does it got to do? It's got to go search for the key and all that stuff, and that's the bottleneck. And we got linear time out of the deal in the worst case because our table looked like that. Oh no. There could be a better way. What do you think that you could do to improve the worst case running time of looking up a key value pair in a hash table? Because right now, in the worst case, we've said that it's linear. Does it have to be? So that's my question for you to ponder. So please get into little peer instruction groups and say hello and try to elect a leader and write down an idea to maybe make it a little bit faster for looking up at the expense of maybe some other operations. That's fine. We care about, let's optimize lookup, because usually you're gonna look up more times than you're gonna insert most of the ways you're ever gonna want to use a hash table. So let's try to optimize lookup and the worst case complexity of it. What could we do to make it better than linear? All right. Questions about the question? All right, go forth. Try that. Think about it. Don't look at the next slide. If you got the slides out, I want to see what you think. Another minute or so, let's say. All right. Another few seconds to finish the thought. Press submit if you can, and we'll take a look. Okay. Let us see. Woohoo! Dun dun dun. Nice. You could make it worse or you could make it better, technically. So quadratic would make it worse, right? That would be like n squared. But I like this idea of group 14. Very nice. Very nice. Let's go there. Let's think about that. Thank you. So I think that would be a good idea. What if we gave some sort of, first of all, we don't have to use a list of elements. We don't have to. Because you can't really, it's hard to sort a list. Like sorting seems like a good idea because then I could do binary search, right? Yeah. That'd be wonderful. But you can't really do binary search on a list anyway because you can't go to the middle. But if you made it a vector of pairs rather than a list of pairs, then it would be fine, right? Then you could sort that all day long by the key. So that would be the easiest thing to think about with our current knowledge of data structures. So like you didn't have to use a list. That would be at the expense of other things, maybe space, some time for the other stuff. But you could have done something else because right now we're kind of forced to use linear search because we got a list, no matter even if we put it in order. So lists, well, we just kept pushing back first of all. But even if we sorted that list, we couldn't go to the middle anyway. So what if we sort? What if we stored a sorted vector at each index, sorted by the key of the stuff that's inside? Ta-da! Something like that. Apparently this is already in sorted order. Nice. Imagine that was a vector instead. And, well, we would have to pay the price with insertion, wouldn't we? Because you push back, you try to put it in the middle somewhere, you got to shuffle stuff over. So the complexity of like doing a sorting algorithm is about n log n in general. There's probably fancier ways to make it work with insertion and like keep it sorted. But like n log n to call sort, let's say, if you ever want to do that. But then that would make insertion more complicated. It would make insertion a little bit longer. It's not linear anymore. It's n log n, let's say. And then lookup turns into logarithmic time, though. And so that's a trade-off that maybe you want to make, because a lot of hash tables, I think you can imagine, like you make a phone book, you put everybody in the phone book, sort the stuff after you put everybody in, and then like you publish the phone book for a year, and like everybody's just going to look up for the rest of time. So usually you're going to look up more often than you're going to insert. I think you can imagine like that's what you're going to want to use a hash table for, looking up much more often. And so that may be a very good trade-off for you. It's up to you, okay? So yeah, there's also more data structures that we could have used that would give us better insertion times as well as lookup time. So maybe keep this idea in the back of your mind, because we're going to learn about some more stuff that could be used here. It doesn't have to be a vector, doesn't have to be a list, there's other things. So yeah, that's food for thought and a cool idea. I hope you see, like that's very CSCI 41 of us to think about that. That's why we went there. So yeah, any questions about any of that before I switch gears to the other way that you could do hashing? You could use the list, use open hashing. There's also closed hashing, where you're forced to use indices and find a new one if you're the one you're looking at is taken. Are you ready for that? All right, so I'm not going to force you to implement this in this class. CSCI 26, if you take my class, I'll force you to do it there. But closed hashing is the opposite of open. It's like you've closed off, the table is all you get. Did I have a drawing of that somewhere? We will find it. I know I drew it somewhere. There we go, closed hashing. If you have a collision, you got to put it somewhere else. You got the table only. You're holding key value pairs at every index of your table. All right, it's called closed hashing. Boop. So let's go there. Let's think about it. Let's say, just for concreteness' sake, we've got, I don't know, we're inserting something into our hash table. Closed hashing is where all you get are indices of the table. All you get. Can't put it in a list outside or something. All you get are the indices of the table. Oh no. So that means if, let's say you insert something like the very first key value pair, like the hash function takes it here, you put it there. Put the key value pair there. That's fine. And then you come back later and you're like, I want to insert something else. And the hash function takes you right back to this index. Collision. Oh no. We cannot put another thing at that index, and so we have to have some strategy of finding a new open index. A very simple strategy is just like, all right, go look at the next index after that, see if it's used. If it's not, put it there. That's an easy strategy, right? Question?
Is that how like emails work or usernames? Because they can't be the same.
Potentially, I would say it depends on what you're asking about. Like when you're signing up and you're trying to, like, how does it know that your username, the one that you just typed, was in use?
Like, is that why you can't or I guess I use it, yeah.
No, I just think that, I mean, you can't share emails. That's what it's doing. But I think when it's checking that, there's a database somewhere that could have been stored as a hash table, if that's where your mind is going. But most likely the database was stored in like a sorted order, and so it was really doing binary search deep down. Was that username in use? I will binary search for it. It's like a little phone book of emails rather than phone numbers. Yeah. Does that make enough sense for now? Yeah. There's something there, I'm sure. Other questions? So if it's in use, we gotta go looking for a new one. And if that one's in use, oh no, we had a hash function that took us either here or here. Where do we go next? You're allowed to wrap around, like, try this one now. And so if you had a bad hash function or a lot of collisions or a small table, you'd be trying to find a new spot for a while. See that? That's not good. That's a downside if your hash function's bad or your table's small. So that's closed hashing. We have decided to keep everything in the table. Every index holds a single key value pair. How do we deal with collisions? There's only one way, right? You have to find another open index. Go looking for one. All right. Sadly, closed hashing has synonyms, and one of those synonyms includes the word open. So try not to get too confused. This still confuses me. It's disgusting. So closed hashing, some people call that open addressing. And I honestly forget why. It's like you're going through the table and the way of finding where to go, it's very open, maybe. I don't know. You're going and looking for a new spot. And you're giving up on the original one very, very quickly. Something like that. I don't know. We can go look that up. But I will call it closed hashing and open hashing. Let's not get too confused about those things. But all right, here is what I just said in like slide form. If you collide, you're trying to go here, you collide, go look at the next slot. That's called linear probing. That's the most simple one. So let's spell out exactly what that means. So the hash function, oh gosh, I don't want to do this. Let me draw a sample table. This is my vector v. It is a hash table, and we're doing closed hashing, which means that every index holds key value pairs and nothing else. Something like that. So, okay, you've got a hash function, and I don't know, there's some stuff, some key value pairs in the table. Just be like inst, 0 to 42, 1 maps to 43, 2 maps to 44, something like that. And you've got, I don't know, you want to insert the pair, like 3 maps to 45. It's my silly example. So you're like, all right, 3. I will hash the number 3. That's where I need to go. All right, that'll give me an index. So I will hash, hash. And that gives me index H. All right, that gives me index H. And let's say that, oh no, this is index H. It's in use. All right, that's what's going on. It's being used, and so what you'll do is you'll try linear probing. It's just like, all right, the original hash function took me here. That's where I would like to insert it if I can. I cannot. That index is in use. I will then go look in H plus 1, H plus 2, trying to find an empty slot. Oh no, none of those are empty yet. But you'll keep on going, wrapping around if you need to find a new spot, and that's where you'll put the new thing, 345, right? You'll go and find H plus 3. That one works, okay? You still need to store the key value pairs in the table. I think you can see why, because if you ever try to look up 3, you'll be taken here, and if we did not store the key, it's like, oh yeah, 3 maps to 42, right? You don't want that. You need to, again, play the same game of, all right, that's not the one. Let's do the same strategy until I find the key. Or I find emptiness, which means that the key was removed or never inserted from the first place. So that's what's going on. Okay, does that make enough sense? That's a strategy. It's called a probing strategy of finding a new empty slot in the table because we are forced to find a new one. We cannot share. We can't have them double up. Okay, so yeah, that is how that works. You can wrap around if you need to. Dun, dun, dun. So we say that this is your table. And you've got like this many things and say your hash function took you here, like I want to insert it there. Linear probing would start looking this way, find nothing, no new slots, then wrap around, and eventually you'd store the new thing right there. Okay, so just like a modulus will do that for you. And then finally, with linear probing, with any of these probing strategies, it's possible that the table's full. Yes? You better remember that, because linear probing would turn into an infinite loop if you tried to insert when the table was full, right? So you better keep track of that somehow. That is very important. So you'll need to store the number of elements in your table, as well as the current size of the table. If you use a vector, you can, of course, get size there, but the number of elements you have inserted, you better put somewhere, because if the table size is n and the number of elements is n, there will never be a new index. You'll be stuck in an infinite loop, and that's unfortunate. You'll have to resize your table. You are forced to resize tables with closed hashing. There's no way around that. With open hashing, you just get a lot more collisions. You don't have to resize, but linear probing, closed hashing. Close off the table, storing key value pairs only. You are forced to resize if you have too many things. Okay, so yeah, I think, does that make enough sense to us? I want to have us try to draw it together. So let's say a concrete example, same stuff that we did before. just the different kind of hashing. So we'll do closed hashing this time. Let's make a size 5 table. So I've got 5 indices from 0 to 4. And we're going to have integer keys, string values. Our hash function is mod 5. And we want to insert these key value pairs. I'm going to do the first one, and I want you to try the rest, please. So, all right, 5 maps to high. The hash function will take us to index 0, because 5 mod 5 is 0. And we'll go looking at that index. Hey, index 0, are you free for a key value pair? You sure are. Let's put 5 mapping to high right there. Okay? And then we're going to do the same with the other 4, remembering to try the next one, wrapping around as necessary if there are collisions. So, questions about the question? So try to break out paint or a piece of paper. I'd really like you to try this just to make sure you understand it. All right? And let me know if you have questions as you're trying it. And I will be here. I'll give you a few minutes to try that. So we're about to fill up the table. Maybe compare this to the one we did before. Think about how it was then regular connection. Now we got closed. I can't tell if that's a cat or a dog. All right, another minute head start, and then I'll do it. How do I save this? Really? All right. That is my timer. Let's try it. Any questions happen as we were trying it that I can answer before I just do it? All right, let's hash all these little keys first. So 1 mod 5 is still 1. 6 mod 5, oh no, also 1. 25, 0. 12 mod 5 is 2. All right, how's this going to work? Once one collides, it starts influencing the other ones too, doesn't it? That's kind of funny. So, all right, 1 maps to mom. That's going to index 1. That's open for us right now. So, okay, we can store that there. That's fine. Boop. 6 maps to hello. Ooh, all right, we're trying to go here. Oh no, we run out of room, so we'll try the next one. Okay, index 2 is open. I will store 6 maps to hello there. That's fine. 25 maps to blah. You can see how this is maybe not the world's best probing strategy. Because, all right, index 0. Oh, no. Index 1 then. Oh, 2 then. Okay, 3. You've gone over half the size of your table over. And then, okay, that's the open slot. That's what I do. I'll put 25 maps to blah there. And then 12 maps to A. Going to index 2. Sorry, you're going to index 4 now. All right. So does that make sense what happened there? Do we see it? It's going to take a lot of time to look around when you have, bless you, a lot of collisions and maybe a small hash table as well as the culprit here. So if the hash table were larger and the things you're trying to insert are more spread apart, you won't have as bad of a time, but you could end up with looking a long time for a new slot. All right. So, okay, there's that. And I think you can imagine how you're going to search. You're going to do the same thing for lookup. It's like, all right, 12 would go to index 2. I see 6. That's not 12, so there must have been a collision. I'll search the next one. 25. Okay, I don't see it yet. I'll search the next one. 12. Okay, there it is. Give back the A. That's the game you play, right? Until you saw emptiness. Because if it was empty, that means it would have been inserted by now. Maybe it wasn't inserted. All right. That's kind of the algorithm for lookup. We'll get to that. We need to now talk about removal, though. So there's a problem happens if you remove, because that idea that I just said doesn't really work as well. So let's say, oh goodness, let's steal this one. That's a decent enough hash table. Stealing it, putting it there. All right, there's my hash table. If gosh, what did I do? We inserted, right, 3 mapping to 45 as well. Like that happened. Boop. We did all this, right? 3 mapped to 45. We had collisions, and so we ended up putting it here, right? And then let's say we don't like 1 or something. Like let's say that I'm going to remove this one. Like I don't want 1 in my hash table anymore. So it's gone. Now it's empty there. All right. Do you see how that's going to ruin lookup? That's not good. So, oh no, what blue was it? Was it this blue? Yeah. All right. That's going to ruin lookup because you hash to index H. This 3 hashes to index H. It's like, all right, 0 and 42. 0 is not the key I'm looking for. So I'll try the next one. And I see emptiness now. Now that I've removed something, I see emptiness now. And now you think, right, then, that, well, if 3 was inserted anywhere in this table, it would have been placed right there, right? So you give up. You give up early. Do you see that problem there? That's unfortunate. You wouldn't have had that problem had you never removed anything. But now we suddenly have it. Does that idea make sense to us? Because we need to solve it. So you should be allowed to remove stuff, but what do we do? All right. If you see empty space, that means you didn't find something. Like we would have put it there, and I don't see it. So what do I do? So this motivates the need for 2 different kinds of emptiness. So here's the idea. So 2 different kinds of emptiness is what we need now. We need the idea of a slot in our table of a bucket being empty since the start of time. Empty since the start, empty since the start, empty since the start, empty since the start. And then we need a concept of empty, but because I removed something. Empty after removal, let's say. All right. So that's now empty. That's what I meant when I did that. This is now empty. Now empty. That slot is now empty. We made it used to hold something. So it's empty after removing something. We'll call that ear. All right. So let me do some surgery here so that looks better. Boop. That's now empty, and we can mark it as such. All right, that's what we want to do. And now you can use the algorithm again. Now you can be like, all right, 3 takes me to index H. I don't see the thing, so I'll keep looking. There's something there. I'll try index H plus 1, and I see empty after removal, which means that, okay, that could have been the 3 I was looking for, but also something else could have been removed. So maybe at the time of insertion, there was something there, and 3 is later in the deal. So I need to keep going, all right? So I'm going to look at this and eventually find your 3 correctly. Yes? If you're looking for 4 or something, eventually you'll get to an empty sense start, and then you can give up, because then you know, like, all right, that slot's been empty this whole darn time, and therefore, if it was inserted anywhere, it would have gone there. Yeah? So you can give up at an empty sense start, but you cannot give up at an empty after removal. It could have been the thing you were looking for. You got to keep going, though, because maybe it's not. Does that make sense? Questions about that algorithm? You'll read more about it in your book. I won't make you implement it this semester. But yeah, that's a problem you have to worry about because you might run into it. All right? You have to deal with 2 kinds of emptiness now, and I hope you see why. Any questions about that before we go to a different probing strategy, a better one? So you can kind of see how you're going to get long chains of things with linear probing. There's a different one. There's a couple others. So I'll teach you 2 more. Let's do one called quadratic probing. And this one, what it's going to do, like the other kind of probing strategies that I'm going to show you, you're going to try to jump around the table, not just like keep everything localized. It's going to try to jump around. All right. This one's going to use a quadratic function to do the jumping. So again, you've got a hash table. All of this only matters when you collide, right? If you can put something in the slot the hash function's taking you to, like index H, put it there, right? Just put it there. That's fine. But if it's taken, then you got to try other places. So this is a new strategy for where to go next. All right. So C1 and C2 create a quadratic function, and they're constants that you choose ahead of time. They can be anything. We'll choose, let's say, my example, C1 and C2, they will be 5 and 7. That will generate a quadratic function that we can follow to tell us where to go next, all right? And I is going to be this is a formula of where to go next. I is the, how should I explain it? I is just the round you're on right now. So I equals 0 means I am looking right now in the very first place I could ever want to look. That's where the hash function takes you. So when I equals 0, all of these go away to 0, right? That's the very first index you look at. All right, that's the round of probing. Let's say, well, that's what I means. All right, what round you're on. So when I is 0, just like go try index H. But oh no, this one's in use. All right, let's say we're trying to insert and we again are trying to go to index H. So when it's zeroed out, that just takes you to the first place. When I is I is 0, that's your first slot to try. It's just the normal place. So when I is 0, you're going to go try index H. When I is 1, look, okay, that one's in use. I want to try another one, try another slot. Then you start, and then now C1 and C2 start mattering. You're gonna go to index H plus 5 plus 7. You see that? And that's going to help you jump around, trying to not like keep everything clumped together. So that's quite nice. Then you'll go to index H plus 12. All right? That's supposed to be an H. Cool. And if there's something there, then again, you try the next one. Like, all right, tried round 1, or now try round 2, or I is 2. That's the next round of probing. So, all right, then you'll go to, now the quadraticness comes into play here. Then you go to H plus 5 times 2 plus 7 times 2 squared, and that's what? H plus 10 plus 28. Then you try this slot over here, right? You're jumping around even more. H plus 10 plus 28. Something like that. That's an H. And then you put the thing there. And you just keep on wrapping around. You do mod size of table because this is eventually going to be a very large number. Just like let it keep wrapping around the table to get to a valid index. And that will help things from like clumping together, keeping and being all localized, and that should help. All right, that should help not having to like search through a million things all at once because they're going to try to like jump around. And I hope that makes sense. Any questions about quadratic probing? It's another strategy. It's trying to make sure we don't like keep things too close to each other. Trying to split up things in the table, spread it out. So yeah, I've made a little example for us. Let me bring that example and also another one that I'm going to use later in. I need to copy it. Here, we also want Shakespeare.txt for later. We also want that one. All right, so a few things. We'll do quadratic probing first. So, okay. Here's my silly pre-programmed example of quadratic probing. I will try to explain it. This code you should be looking at later, though. It's a lot. So, all right, here is my hash table. It's a vector of key value pairs. That's what a hash table in closed hashing is, right? It's a vector of key value pairs. And also, we're marking was it empty or not, if there isn't a pair in there right now. So my struct pair, it's a vector of pairs, is my hash table. And what is a pair? I've put 11 things, 11 buckets, prime number. Here's what a pair is to us. So it's got a key value if you want to put something there. And then it's got some marker booleans for has this element ever been deleted before? So that would mark empty after removal. And like, is there a value here right now that would mark empty since start? So right now they're all going to be, by default, empty since start. Does that kind of make sense? Marking those things. And it has not yet been deleted. And if you ever insert something, you have to turn that back to false again, if it ever was true. And then here are the constants we can pick again, 5 and 7, those are fine. And then here's my silly little hash function that's going to cause a lot of collisions on strings. And so, yeah, this is me inserting stuff, looking up values that are sometimes there, sometimes not there. You should be allowed to update as well. So let's just watch it work, and then I'll talk about why it works and how. But it is a hash table. Like, you put the things in, you get the things out. Things that aren't there, you notice that. You're able to update things as well. So let's do lookup first, maybe, honestly. Or do I want to do insertion? We can go in order, that's fine. So, all right, to insert into a hash table, it's a vector of pairs, right? A key value pair you're trying to put in there. So your goal is to go to some index, right? The very first index you try is the one that the hash function gives you originally. So that's your H, okay? Go there first. I'm going to call IDX the index I'm looking at right now for my current round of probing, and I is 0, all right? And so what you'll do for the very first round, you're just going to like go to that actual index, index H. Go there, see if there's a value right now. If there is, if that's true, and the key is not the key you're looking for, because if it is the key you're looking for, you want to update it, right? If that's not the case, then you just got to keep looking. It's in use, or it's not the key you're looking for, okay? So that's the goal. Something like that. And sorry, it's in use and the thing is not what we're looking for. So just like keep going. Next round of probing. What's the new index that we're trying to look at? It's always going to be the original H plus C1 times I plus C2 times I squared. So they're there. Wrapping back around the table because that's going to get large. Okay, so that's what you do. That's how you jump around and find the new slot. And yeah, if you have a table size that's prime, you won't ever get into a little weird loop where you accidentally go to weird places multiple times. So you will try every index. That's perfect for us. And yeah, you want to keep on doing that as long as you don't find something. The second this while loop stops, what's true, right? The second this while loop stops, you're in a spot. You're either in a spot, like you want to negate this condition, right? So the second this while loop is done, you're where you want to be, essentially, right? Either you're not in a place with a value here right now, so you're in an empty sense start location, right? That's what would happen if that first thing happened to be false, because that would stop the loop. Or you're at a slot that has a value, Like this is still true, but this is false, right? That also would have stopped the loop where the key is what you wanted to change. Yeah. So no matter what, you are now at IDX is the index you want to mess with. You want to put your key value there. If it was brand new, you want to set the key as well. So just like do it all at once is fine. Otherwise, you just want to update the value. So it's either this or all three of these. Just might as well do all three all over again. So you say all these, set the key, set the value, and then say that yes, there is something there right now. If you didn't think there was already, put it there as one there. So this will also do the update, just kind of because these will already be set. If it was just an update, you're just changing the value at that point. But if it was a brand new thing, you got to set the key and the value and say it is in use. All right. So that is insertion. Does that make sense? So you're using this kind of loop and this algorithm, this formula to determine which slot to go look at next, which bucket. All right, and then lookup is exactly the same. It's like just go to the indices, see if you can find the key. So again, you start at the hash of the key. That's your first index to try. Your I is 0 because that's your it's your 0th probing round. And again, you're going to keep doing this. Like, all right, while there's a value right now and it's not the key I'm looking for, like it's empty since start. It's not empty since start. And it's not the key I'm looking for. Keep on I++ing and trying the next index according to our formula. The second this while loop stops, either we're at a place, right, that does not have a value, that's empty since start, or we're at a place that is in use and it is the key we're looking for. All right, we've got to figure out which one, because either, like if we're there and it's the key, then we return the value, we're good. Or otherwise, that was an empty slot that was not in use, and therefore we want to return the fact that we did not find the thing. Okay, we did not find it because it would have been here by now if we got to a slot that was empty since the beginning of time, something like that. All right. Technically, this is kind of wrong because what if the key was deleted? Like you just got to the slot. No, that was empty after removal. You could be doing better here, but I'm lazy. All I care about is showing you this. So yeah, questions about any of that? Because that's what's happening. I think you can imagine that's going to work. We saw it work, and yeah, maybe a good practice would be fix this, do this right, and then maybe add removal. That'd be a great way to practice these ideas if you want to. But yeah, that's quadratic hat probing in a nutshell. Any questions about that before I show you the last one? There's one more kind of probing strategy that everybody needs to learn. It's probably the best one of the three. This one's called double hashing. So this one's going to jump around the best. All right, there's not even going to be quadraticness involved. It's still going to jump around better than quadratic probing. So this time you need 2 hash functions for all your keys type. All right, you can have your original hash function. Let's call that h1 now, and then you need some h2 that's different, that gives back another kind of number for values. It works in a different way. All right, and this has a very similar probing sequence where when I is 0, when I equals 0. This formula causes that to go away, and you go to the original hash's place, still, mod size of table. But then when I is 1, you start using the other hash function. So yeah, your first index is just the normal original hash function on the key. And this is going to let you jump around more, even though there's no squaring or anything going on. It's cool to think about. So like you got a vector. Because it's going to jump around differently for different keys, because that other hash function is going to give you a different value for different keys, rather than picking constants that never change. You see the difference? That's why it's going to jump around more. That's beautiful. So yeah, when I is 0, you'll try your first index, be like, that's h1 of key. Go there if you can. That's when I is 0, you just go to h1 of key. When I is 1, you're going to go to, you're going to jump around, you're going to go to h1, maybe over here. That's h1 of key plus 1 times h2 of key. Like maybe that one is in use, but this one wasn't. You go there. If this one was in use, you try h1 of key plus 2 times, right? Plus 2 times h2 of key. And so because hash functions they should be giving back different values for different inputs, it's going to jump around differently for each kind of key. Isn't that nice? In theory, at least. And that's going to have it look a little bit different because quadratic probing, you know that if you started at index H, you're going to try the same chain, right? You're going to try the same chain of things because it's the C1 and C2 that are moving you around, and those are fixed. But for double hashing, the way that you jump around depends on the key now, which is great. And that's it. It should be a different value because the hash function gives back a different value, right? So you get more variations out of the deal. And even though it jumps around in a linear fashion, this is a graph of a line, right? It's still going to do better. It's going to be more wonky and weird and lovely. So, bless you. I think that's what I wanted to say. Questions about double hashing. It is sometimes hard to find another hash function. Your book will talk about this, though. There's some good ideas. But yeah, I think that's what I wanted to say about all of that. Are we ready for a couple other topics that are only slightly related? Still hash table stuff. Because we do need to talk about resizing. We should probably deal with that because that's kind of expensive if you think about it. You have you want to not end up in the case where you do have such a tiny hash table. You got a lot of values. You want to resize eventually. Let's talk about when. All right. At least when. You can imagine how is going to be disgusting because you got to make another table. It's very long. You got to go through every key value pair in your old table and like insert it all over again, which is it's going to take some time. All right. So yeah, let's talk about it. So eventually your hash table will get full. If you're if you're closed hashing, you are now in trouble. You better resize, or you'll have in either case, open or closed hash, you're going to have a ton of collisions if you start inserting a bunch of stuff in a small table. So you might as well make it a little bit bigger. It's time to resize it, just like for vectors. You can do that because maybe you're going to make a hash table out of a vector. That's fine. Again, just like vectors, if you play the game right, you will not affect your time complexity. Just like you want to double the size maybe each time. As long as you don't resize too often, your time complexity on average will stay the same. That's not a CSCI 41 topic, but I might as well say it so you can look it up if you're interested. That's cool. But usually here's kind of the idea. You want to resize a hash table of size n to the next, like you've got n things in it. You want to resize it. If you notice you want to resize it, you want to resize it to the next prime number that's at least as big as 2 times n. So you're doubling it and then some, potentially. All right. We know why prime numbers now, at least as big as 2n. So a lot of hash table implementations, they have a big long table of prime numbers. It's trying to find the next one, binary searching for the next one. That's a thing. And the way that you, or the way you notice you want to resize is usually you're keeping track of what's called a load factor, and that is exactly what you would expect. Like how much is this table in use right now? The number of items divided by the number of buckets in your table. All right. So you usually want to resize when you get a little bit around like 3/4 of the buckets are in use, right? Number of items over buckets, like 0.75 on your load factor, then resize to make it at least double. And so that'll bring it down to like less than 0.5 for sure. That's great. And I think that's what I wanted to say about resizing. It is a little complicated. It does take some time to do the resizing, but as long as you don't do it too often, it won't hurt you in the average case. All right, and that's another example of what we called amortized analysis, which you might want to look into. One day you'll be forced to learn that. Same reason for vectors, why pushback is still constant, which is interesting to think about. Amortized constant, we say. So yeah. I think that's all I wanted to say about resizing. Does that make enough sense? So try to be like vectors. You'll get the same kind of good stuff that we talked about with vectors, but we care about primes in hash table land for mathematical purposes. All right. So yeah, I think the last place I want to go is just like show you, okay, how C++ does it, right? You've used this already. This is C++'s version of a hash table. Unordered map. They've got a bunch of hash functions built in for types that we know and use already, like strings and int. So like go look at there's a way to go and find the hash function on strings for C++. Go see what they were doing. I have no idea where it's going to be, but C++ string hash function in the actual standard library. Probably on GitHub somewhere. find it for me? Whee! I want to find this one. Yeah. Where is it? Whee! GitHub. Hey, there it is. I think. No, this is somebody else's standard library, maybe. Or they just took it out. I don't know. Hash. It is a little... Okay, they're doing it with just the bytes. It looks like they're doing some weird stuff with... what's it called? You guys remember your bitwise operations? That's what they're doing, it looks like. And they're doing weird stuff. Which is cool. Nice. Oh, please do attendance if you have not already. I want to stop that. Okay, so yeah. There is unordered map. That's what it's called. Let's go to the documentation. Unordered map. Dun, dun, dun. Unordered map. Associative containers that store elements formed by a combination of a key value and a mapped value. What do you know? And it is... Why is it so long? I don't know. It's got a key type and a value type. Key type and a T type for value. So it's got two. It's templated in two things. And also more. You can give like the hash function if you want to make your own hash function. Like it takes that too. So look at all the cool things. It's wonderful. You can click on things. Like the constructor you can click on. It's like an example of it. But there it is, mapping stuff. And iterating through, that's not very useful. It's .at is their lookup. It takes a key type, and it gives you a mapped type of value back. So there it is, like, give me things. You can use it to update as well. But yeah, let's go through it all. Before we get into all that, like, you know that there's an unordered map and also a map. So this implies that map must have order, doesn't it? And it does. You remember iterating through a map and it got you stuff out in sorted key order? It was storing it in that way. Map must have, map just by itself must have order then. So, all right, unordered map time. So let's look at the documentation we have a little bit. It has an iterator, so there is a way to go through every mapped value. You're just not getting, you have no guarantees about the order in which you're getting things back. So like there is a begin end, like go through it, but who knows? You can actually get at individual buckets. That's kind of cool if you want to do it like that. But yeah, you can just iterate through all the things. It gives you pairs, but you have no control over the order of what's there because it's placed in some weird hashing way, right? Just going through the buckets, essentially finding stuff. And you know that you have no control over that. So I think I have just a short example of that, might as well. But it's exactly as you would expect. To insert stuff into a hash table, assuming... There's two ways, actually. There is insert, which takes a pair of things. You got to give it a pair. There's a make pair function. It looks a little weird. You can use these little braces to do that if you want to. But like you can say make a pair of these things. And that, I think, should also update. Inserted only if the key is not in there already. So that, honestly, is actually not going to update. So insertion only inserts. And the other one I want to show you is in place, which is a bit cuter. Like you can, it makes more sense. Just like insert a key and then a value, just like that. But I think also, let's see. Yeah, I think also this one's not going to insert if it's already there. All right. It looks like it's saying it's only taking place if no element in the container has a key equivalent to the one being placed. Yes. And so the update is done only with .at. You better check and see if something's there because in place is not going to like overwrite like I've shown you in my little functions that do that automatically. So interesting to think about. That's a trade-off they've made so that you don't accidentally update something maybe. Unordered map. So let's include that. Let's do strings as a key or a value. As a key, maybe. So I will make an unordered map from strings to ints. Here's a phone book, a legitimate phone book with constant time on average lookups. Yay. And so one way to insert, the easiest way, you say .mplace. I forget why it's with an E. We can look that up later. But it's kind of like calling constructors on things to build things. So I want to insert the key value pair Lawton mapping to my phone number, 8675309, something like that. All right. And so that'll insert, if it wasn't there already and it's not, that value. Boop. We can do another value. So that mom maps to that number. And yeah. Now, to update or get something out, it would be at. See out my map m.at Lawton. You can use that as well to do an update. You can be like m at Lawton equal or plus plus if you want to. Like that would work. You're allowed to mess with it as well. All right, but let's not give it the same number. Let's do like, I don't know, minus minus. There. So you can get the values back, Lawton, mom, if they're there. If they're not there, you get an exception and a runtime error if you don't catch it. So there they are. It got updated. So update, you got to go through .at to get it out or to edit it. If you have something, you try to go somewhere that's not there, like dad, it's going to throw an exception. It's going to throw an out of range exception, which I guess is as good as you can think of. That's the best word we can think about. It's like out of range, that just means it wasn't there. And so you should have checked before going there. There's a way to check, all right? So the way to check, the standard way to check is they try to make the words the same for a bunch of different containers. And so that's why it sounds a little weird for maps and hash and unordered maps. It's called .count. You can also do .find, but .count, it gives you back essentially an int where you give it a key and it gives you back how many things of that key were in the hash table. We know that hash tables can only have 1 or 0, but count exists for other containers, and that's why they kept calling it count. All right, so it's only ever 1 or 0 for our case, which is nice to think about. And so that's what you do. You do like an if statement, like, hey, before you even try to go places that you don't know are there or not, you just do .count. .count Lawton, .count mom, .count dad. And you know that 1 is true and 0 is false. So this could have been like if, just if that, essentially. If that in an if statement. It's like in the body you use it, go to .at, it would work. Something like that. Whee. So yeah, true, true, false. You can go to the places that exist. Just like kind of cut that off. Make sure you can't go there with an if statement or something. So yeah, I think that's what I wanted to say. You can iterate through with iterators. You'll get back, just like for maps, you get like a first and a second. You go through pairs of things. You get firsts and seconds to go through, and you have no control over the order. So yeah, I think that's most of what I wanted to say for unordered maps. So there's a default hash function for strings that it's using. Yeah, any questions about this? I forget what kind of hash table it is. I believe, if I remember correctly, it is implementation dependent, but I think they're using open hashing. And so that's why they're not ever asking for like a second hash function if you wanted to control it yourself. Because it can take a hash function right here. It doesn't need 2, so it's definitely not doing closed hashing. But yeah, I think it's implementation dependent. So who knows? But I think last time I looked it up, it was doing open hashing with like lists or something along that line. So yeah, I think that's what I wanted to say about that. I don't know. How do I want to do that? I think that's fine. Yeah, I have just a silly example left. Would you like to see that silly example? Just with hash functions, like one thing that's useful, that they're useful for. I would like to implement autocomplete for you. So I have a pre-made example. It's a little ugly. I'll try to go through it as much as possible. But before AI, before our phones could do AI, you could do autocomplete on your phones before, right? You start typing stuff and it has little suggestions, and then even if you don't type something, it'll try to fill in the next word, the next word, the next word. Remember that? That's a thing. Let me show you that algorithm. It's not hard to think about. It is like this is what phones used to do for autocompletion before AI was involved. It is technically still machine learning because it's kind of learning how you type and how you say words, right? It was doing that. You just like tap the next thing. It's going to talk like you, but it's going to sound weird, of course, because it was not as fancy back then. But here is one way to do it. It's an autocompletion where having typed 2 words, it will predict the next one. It'll always look 2 words ago. What are the 2 previous words? And it'll use that to see like what should I predict as the next word? What do you usually type after those 2 words? Essentially, that's what it's going to try to remember. All right. So, for example, let's say that this is the only text you have ever typed in your text messages, and like that's what it's learning from. So it's going to save the fact that it's going to scan through all the things you ever typed, and it's going to remember like, okay, the quick after that you sometimes type brown. It's going to remember that. So remember that all the 2 previous ones can keep track. So like, all right, if I ever see the quick, I can predict brown now. If I ever see quick brown, I know that sometimes after that you type fox. And sometimes you type multiple different things after that, right? So that's what it's going to remember. Brown fox, you see that? Predict jumps, stuff like that. Okay, so that's what it's going to see. And like you're going to type multiple things with multiple words. Like I think you can imagine like at the or something. You'll type that so many times. It'll just remember all the things you type after that, right? It'll remember all the different things you say after that and use that as its prediction. All right. And so, for example, with letters, like if you've typed AB a couple times before, it knows that sometimes you type A after that, sometimes you type D after that, and so it'll use that in its predictions. Like, all right, you've typed AB so far and you want me to autocomplete. Well, I'll choose from my knowledge, just like randomly, I'll pick A or D, something like that, or give you the options. All right. So if we want that, right, what we want to store then is a hash table, and sometimes you'll have to like clean this up just to make it normal, like you see capital the, remember that as like maybe lowercase the. Like you'll want to do that so that you have more firepower, like because that's important. So you might want to clean up your sentences as well. But yeah, this is kind of the algorithm we're going to need if we're going to store this kind of stuff, like pairs of words and then the next prediction. It's going to be, and then maybe multiple predictions, right? A or D. Our hash table is going to be pairs of strings, right? Mapping to like vectors of options that we want to use as our predictions. Does that kind of make sense? The types involved there. They look a little weird, but it's kind of cool. So you see those things, predict those things. And so as we're generating this auto-completion table, we're always going to keep track of the last word, the last word, 2 words ago, and then like a vector of things, a vector of possibilities to predict given those 2 previous words. All right. So I'm going to make an unordered map that looks like this. I'll make a word pair type that is just a struct that wraps around the idea of holding 2 things, holding two strings, and then a vector of strings at the end. That's the value type. What are all the things, initially empty, of course, what are all the things that I want to predict? Like how many, what have you typed before after that word pair? I'll save those things and choose randomly then. Randomly choose from that vector to predict the next word in my auto-completion, right? So if you'd like to learn more about this, the fancy term for what I'm about to show you, it's called Markov chain, that's a dude's name, Markov chain text prediction. And it's easy on memory and space, and so that's why it was easy to put into phones back then. So here, let us do that. Dun, dun, dun. Here's the file. Oh wait, there's something weird about my Vim. Let me just open it up again. So here is, first of all, the entire text of Shakespeare. What I will be doing is making this autocomplete and sound like Shakespeare. That's where we're going. Have it type like Shakespeare. But here's what we were doing. A word pair is like 2 strings. I won't go through all of this. Here's my hash table, my completion map. It's taking word pair keys to vector of string values. Dun, dun, dun. There they are. And I also, when you make a hash table that has a key type that C++ has never seen before, like I made the word pair type, it needs to know how to hash that. It needs a hash function. And so I have to also give it the hash function if I give it a type. I have to make my own hash function. And so here I am making a hash function using the built-in string hash. I'm essentially like, I'm adding up the string hashes of the two words inside of my word pair thing. So I'm using the string hash function inside of there. This is just the one that's baked into C++. So don't worry too much about that, but that's necessary. And that should be most of it. Do I need to show you any of these other things? An equal equals operator. Here I'm converting things to lowercase because like I want to use capital the and lowercase the. Like that shouldn't matter when I'm predicting things. So, like have those be equivalent. So I'll make them lowercase. Convert to lowercase does that on a string reference. And then here I am. I'm taking a file. I'm going through it. I'm always going to keep track of my current word and then the two previous words. So you kind of do have to read two words in first. There they are. Make sure they're lowercase always. And then always get the next word. Then you always just keep shifting things over as you're reading more. It's like, all right, you got the next word. You got the two previous words. Convert that new word to lowercase. And now save that you've seen those two previous words and this one came after it. So, all right, this is how you think about that. You got your completion map. That's your hash table. If I have not seen these two previous words before, then I can emplace, right? It only works the first time with emplace or insert. Emplace that key, which is the last two words, to this next one, next word there. And it's just a vector of the one thing, because that's the only word we've ever seen before that came after these two previous words. Otherwise, we already have a vector for these two words. Push back to it, that word that we've seen before. If there's duplicates, that's fine, because that just means you said that word more often than other words after those two words, after the two previous ones. And then as you're reading, of course, you got to shift them over. The 2 words ago is now the last word, and then 1 word ago is now the word you just read. Just like have that loop continue throughout the entire file. And then you've got a completion map. You've got 2 previous words, always predicting the next one. And so if you pick some random word pair, here I am predicting or going somewhere in my completion map, randomly, get to 2 words, right? Here's a pair. I'll do that and output that one. Like that's my first, just go to a random place in my completion map. That'll give me 2 words, give me the key, right? And then, like, I'm going to build up a sentence of 100 words using my autocomplete. So, like, I've got 2 words. I've just gone to a random place in my completion map. There's 2 words as the key. And then you know that after those 2 words, we've predicted something, and we can just keep going, right? So 98 more words to go. There may be nothing left. Like there may be, we may come to something that has never existed in Shakespeare. Then we stop. We have a shorter sentence, but usually we can keep going. We always have, most likely, we've got our 2 previous words. We've got a vector of all the options that we could have that Shakespeare used after those 2 previous words. We've got a bunch of possibilities. And then I'll just pick randomly from those possibilities. There's my next word. Add it to the sentence, and now remember what the 2 previous words were ago, just like shift things over again. And then just like keep doing that and predicting using my completion map, like, all right, Shakespeare used those 2 previous words. How? What came after it usually? Pick a random thing from those possibilities, and output my sentence. So that was very, very fast, me explaining that. Read the file. I can help you understand it, but it's kind of silly and cool. And that's one thing you could use hash tables for. Whee. And you could also give it any file. I've made it so you just give it a file name as an argv of 1. So that's your command line argument. So you could like go extract all of your text messages from your phone if you want to. Make a text file, give it to this, and it'll talk like you. Make a 100-word sentence talking like you. Whee. So it's going to take a while to read the thing. But this is what it looks like. It kind of makes sense. Somewhat, but don't look too hard, right? Stay yet another day. Like that was predicted. That's kind of cool, right? He killed me dead. Her cradle. Sometimes there's only one option. It's like it's actually just reciting Shakespeare to you. But a lot of the time it is like these are made up, right? Take up the right opinion. Something like that. Sit thou here, and I'll seek them. Cool. And you can rerun it, of course. And it'll look different. Dun, dun, dun. Get you home the crown. Sometimes it doesn't make any sense, but that's okay. Incite them to their captain, and I attend here. Yeah, and whiles I am for you, great sir. Like that kind of makes sense. And so that's what the old kind of auto-completion was working like, and it's still fun to learn and try to figure out. All right, so I think that's what I wanted to say. Are there any questions about that? Very fun. Because like there's a million things that came after that but it picked a random one.
Yeah.
Picked a random one, and like it sometimes makes sense. That's kind of cute. And so, fun little algorithm with a use of hash tables. Yeah, I just have a couple more things to talk about today. So, let's talk about this as well. So, like, you're going to be tasked in a lab to make your own hash function. I forget if it's the one I'm about to release or not, probably. If you want to make a hash function of something, here's a secret. Just come up with a really good way to make a hash on strings or something. Okay, here's the secret. So like you got a double, let's say you got a vector of stuff. Let's say you need to hash it somehow, the vector of something. Like it's very complicated. You can look it up on the internet. Like people have come up with good algorithms. Your book's going to say some stuff, of course. A very, very simple way is just always get to a string somehow and just have a really good string hash function. Because you can always convert a double to a string, right? You can convert a vector to a string, of course, by like putting commas between the values and converting each value to a string, couldn't you? So like get a string somehow. That's easy. And then you can just hash the string with your good hash function that you've made for just strings. Does that make sense? Like that could be a secret for your lab. So one way to do it. All right. So that's food for thought. And yeah, here's one last slide with some trade-offs that maybe you want to understand and like just some sneak peeks to future classes. So when would you want to do open hashing versus closed hashing? I think standard libraries have kind of picked one of these. I think open hashing is probably the winner. It's easier to implement. It only takes one hash function. But open hashing is better when you want to save some memory sometimes. Like you might have a very high load factor, like the number of indices to the number of elements you want to insert. And that hurts you really badly in closed hashing because you keep looking a lot. You keep looking around a lot. It can turn lookup disgusting. And like you don't want to be forced to resize all the time. Like you have memory concerns. Like open hashing is probably better then. Like you can keep your high load factor. You'll end up with more collisions, but it's not the end of the world. Like it would be with closed hashing because you're usually going to keep finding and jumping around way too many times. So there's that. Closed hashing. When might that be better? There's some ideas. If you're able to keep your load factor small, then it's like you don't have to like go and move around two different things. Because for open hashing, like you got to get to an index and then go through a list or something. For closed hashing, it's just like get to the index. And if you don't have to jump around too much, if you've tried to guarantee that with a small load factor, then it's slightly faster to go places, but it's negligible, but sometimes that matters. And then also because it's just indices, like you can start parallelizing things. If you want to think about multi-core processors and multi-threading, that process is faster because it's just going to indices again. Just like go and find the thing if you can. Yeah, it uses slightly less memory because like you have to add list nodes with open hashing or something of that sort. Slightly smaller stuff. And yeah, there's that. You will eventually implement closed hashing in a future class, at least if you take one with me. There's also the idea of the cache inside of a computer. I don't know if you know too much about what that is, but it's a place that helps you access things quickly, and you get better cache performance, only usually with linear probing and then maybe a little bit of quadratic probing. Double hashing doesn't really work that way, but that might make lookup faster in practice rather than on paper for weird cache reasons. The cache is a fun place to think about. Yeah. I think that's all that I wanted to say. Those are some words that may make sense one day, but I think that open hashing is a good one to start with, and that's why I'm going to have you implement it. Yay. So yeah, I think that's the end of the story. Are there any questions about these slides? We made it. We made it through hash tables. Go us. All right, so I've got a lab to give you. Lab 5. Let's talk about it. That's what I thought. Okay, there's not quite hash tables yet. We want to do decks and stacks. Why not? So here are all the files, given you make file, of course. and we're going to use templates. Yay. So, okay, get all the files. You're going to be making first a deck, all right? You're going to make a deck class using a list on the back end. It's not a list that you made. It'll just use the C++ standard libraries list, so that's fine. So you're going to implement all this stuff in deck.h, in deck.h for once. Because with templates, remember, there is no .cpp file because the code does not exist until you use it. So this is the one time with templated stuff you stay in the header file only. All right. So here is a templated deck. It's a deck of t's. So you want to be able to store a bunch of t's as a deck. You want to be able to push front some t's, push back some t's, pop front, pop back. Peek is what I'm going to call look at the front, look at the back. It will give you back a reference to the thing there. See if it's empty, get the size. And what we're going to use to store our deck is a list of t's. All right, you want a deck of t's, deck of ints, you're going to use a list of ints. So a C++ version of all that stuff. And this is kind of what each implementation is going to look like. You're going to put it in the header file. All right, put it in the header file. This is what the first one will look like. So it's templated. It's a deck of t's push front. Give me a new t. What do I do with it? All right, you're just going to have it affect the underlying list. It's going to be a very quick implementation once you understand what's happening. You're just kind of like handing off the problem to the underlying list, but you're giving access only to these things for the user. Okay, that's what a deck is going to be. That's what you're going to implement. You're going to do it in the header file. All right, you're essentially going to call the list stuff with the same name, more or less. And remember that it's all going to stay in the header file for once. And that is what that one is. Are there any questions about decks? Decks using a list. All right, a list that you didn't make. And then I've got a test deck.cpp file that the make file is going to make for you. Like it'll make, there's a test deck and a test stack. So there's test deck. And I've got just a silly little first test. And I want you to make 2 more once you get mine to pass. But here it is. It's making a deck of ints. It's making sure that the size starts out 0. You push back some stuff. The size is changing. The values are what they should be. And things eventually happen. Okay? So there's the first one. Maybe make a test with a deck of strings or something. That could be another good test for you to try. Try some operations in some order. Come up with some weird scenarios, but 2 new tests, please, of your own. And that's test deck. Not too horrible. And then I want you to use your deck that you just made to make a stack class. All right, see where I'm going with this? Because what is a stack but a piece of a deck, kind of, right? All a stack needs is push and pop to one of the ends, and you can pick which end, bless you. So there's stack.h now. Again, we want a templated stack, and how are we implementing a stack of t's? We will use a deck of t's, one that you've made. Perfect. That's lovely. And we are going to push and pop from stacks, and for pop, our version of pop will give back the value, a copy of the value that just got popped. Then we got peek, looks at the thing, does not get rid of it, but gives you like a reference to it, empty in size, and there you go. And you're going to implement that. And you'll just essentially call deck operations for the implementations of all of these. You'll pick a side, though. Do you want to push and pop from the front or from the back of the deck, right? Because you have options. But all you give is the user access to those things. So that's stack. Does it make sense how we can use our deck to build a stack? So that's quite nice. And then we, of course, can test that too. And so I've given you an initial stack of ints test. Please make some more stacks of maybe different types. You can make a stack of stacks if you want to. Look a little weird, but that's totally possible. Stack of stacks of strings. But again, it's just like pushing and popping, making sure the things give back the right values. So yeah, once you get my test to pass, please make 2 more. Not the world's hardest lab. You don't need too long to do it. So yeah, that's what I want, and that is all. All right, so you're implementing, for once you're submitting header files because you're actually changing those things. You're giving implementations there for once. So you're uploading those as well as the new tests that you wrote, and that's all. All right, not the world's hardest lab once you wrap your mind around it, but templates. They're a little weird. You can put any type inside of your decks and your stacks, and therefore the underlying list that's at the bottom of all of them somehow. All right, so yeah, that's Lab 5 in a nutshell, and eventually there will be a hash tables one, but not quite yet. All right, questions about Lab 5? All right, only a little bit more talking for me. The last thing that I want to talk about today is the fact that we are in week 8. There are what, 17 weeks of classes, I think, if you include finals week. I counted once, but I never remember. Yes, no, 18 weeks. 17 weeks of classes and then an 18th week, which is the finals week. And so we're about in the middle, more or less. Maybe next week we'll be in the middle. And so what I like to do for all my classes is give a little anonymous survey. This will never be traced back to you. It's a Google form. It's not for a grade, of course, because it can't be traced back to you. But I would appreciate your feedback on the class. If you'd like to give me any, you can write as much or as little as you'd like. But like, we're still in the class together. This gives me, if there's something that's going wrong, it lets me see that while there's time to still fix it for you. And of course, it will help me with my future classes and my future students. So I would appreciate your feedback if you would like to give me any. Just like, here's my silly little questions, like, please give me 3 things I should keep doing, stop doing, start doing. What would you like to change about the class, if anything? And what has been your favorite thing so far, so I can highlight that more later. Stuff like that. Yeah, so that is a little anonymous feedback survey. You don't have to do it because I can't trace it back to you, but if you have something to say, I would appreciate you writing it up and submitting. But yeah, I think that's that one. No grade for that, of course. But yeah, I think that is the last thing that I wanted to talk about. Fill that out if you would so desire. And I think that's everything. Any questions about anything at all that we talked about today before I let you work? All right, that is all that I have.